papers I believe which were or are quite important to know maybe, and that we have a bit of intuitive understanding what the field is and where we are moving actually. So it's what I call an AutoML landscape. First of all, why are we sitting here? I think it should be quite obvious, because the typical task of a data scientist, machine learning practitioners, as a researcher and so on, you always have given some kind of data. I simply put one here from AutoML, diabetes data set. You have some kind of maybe cryptic description. Sometimes people put a lot of effort into it, and sometimes it's very shallow if there's even at all a description of that. And then your task is actually to deal with that somehow. Maybe you know actually a bit of what kind of attributes you are, or maybe some kind of describing features about your data set. But then you, as the one applying machinery, has to figure out how to do everything with that. And that means quite a lot, because I don't know whether you can do that, but for me it's still hard, even as a machine learning professor, to then decide on the fly what kind of data preprocessing you need, what kind of visualization, missing data handling, the best model maybe, best visualization techniques, best hyperparameters. There's a lot of things to decide, right? It's not, unfortunately not the case that we can simply press a button and say, here, come on, here's a data set and do something with me. Machine learning involves quite a bit of stuff. And I know that some students these days are always coming to me and say, yeah, come on, ChatGPT can do that for me, or Gemini, or Claude, or whatnot. I tried it out, and that data set, it produces complete bullshit, actually. Even if it's at all producing workable code. So it's unfortunately still not so easy to do that. And we hope actually that AutoML can contribute to solving these kind of things. So what AutoML actually enables you to do is increasing efficiency, because for some of these, maybe you have a very good intuition on how to decide what kind of model do I actually need. For example, of course, you should know that you need different models if you're doing classification, whereas you're doing any kind of sequential data, right? Simply different kind of model types, you already have a gut feeling which direction you should go. But later on, for all these little gritty details, maybe you don't know that actually. And the AutoML can help you speeding up, making very efficient ways and figuring out what are good settings, what are good decisions, what are good techniques to be applied here. Also, the nice thing is doing that in a more or less systematic way, right? Because a computer is doing now jobs for you. It's not you deciding based on a gut feeling a lot of things, but actually the computer can do a lot of things for you, which on the one hand saves you time, and also quite nice that it increases reproducibility, which is in fact quite important these days if you think about the UAI Act, which now requires that you document and make things reproducible. Why have you done certain decisions? So also from a legal point of view, you need to do that. And of course, if you're writing a paper, you also would like to be reproducible. Overall, that enables that machine learning is used by more and more people, right? It's not only as, I don't know, 10 years ago that only computer scientists can do that, but now actually many people can apply then machine learning by using AutoML techniques, by being more efficient, by taking care of a lot of design decisions. Nevertheless, there are a lot of challenges actually being involved in doing that. First of all, for different data sets, there's not one single silver bullet, right? So we always need specialized solutions, even these days, even with transformer models taking care of a lot of things. It's not even the one transformer model, right? Even there are a lot of little details you have to adjust, you have to figure out how to do that to really get to optimal performance. Furthermore, with larger and larger models, it's also getting more and more expensive to try out different kind of hyperparameters, different kind of techniques, and so on. So it's not like we can try out thousands or millions of different kind of configurations of our system, but we have to be efficient in making decisions, right? That makes AutoML, of course, also very hard. Then all these kind of mathematical relationships between design and performance is simply not known to us, right? It's quite a black box problem where we can try things out and then observing performance, but we don't have any kind of gradient signal. We can approximate these kind of things, but given it's not by default. And that's what I need. It's a highly complex space. It's not complex in the sense of billions of parameters, but it's complex in maybe tens or hundreds of hyperparameters, which can have different kind of types. So maybe they're categorical, maybe they're continuous, maybe there's some kind of hierarchical structure between them, and so on and so on. So that makes AutoML quite complex and not super easy to do. But the nice thing, the AutoML community did a lot of things over the year to tackle all of these problems. And that's my overview graphic for a lot of different kind of ideas the AutoML community came up with. And I would like to go through that very quickly now. Of course, we always think about this kind of very trivial, more or less process. So, okay, there's data given to you. If you have to do any kind of pre-processing, so somehow transforming the data, then there's some kind of an AI model or machine learning model or data science model, whatever you like to call that. But there's a model, so doing any kind of prediction, let's say, and then you're getting any kind of insights out of that, depending on your application, right? That's the typical workflow. We always think about that. What does that mean in practice? So first of all, we have to take care of the data pre-processing. Of course, we are not quite on the side of how to collect data. We always assuming data is somehow collected. Maybe data is not perfectly, right? Maybe the quality of the data is not perfect. And the AutoML community also worked on that in different kind of aspects. I picked here some papers actually which dealt with data augmentation, saying, okay, if you, for example, care about images, you can flip them, rotate them, crop them, and so on. And you need to know actually what to do actually for what kind of data set that you are then invariant to all these kind of transformations that then your, for example, image classifier can work well in practice. So the AutoML community and the people worked on different kind of techniques to improve that part. For example, also the recent paper by the colleagues in Freiburg also saying, okay, you can do all this kind of cropping, rotation, flipping, all this kind of data augmentation, but which one actually is important then to train on, and where, for example, then developed that with selection approach to figure out what are the best pairs actually we need to train on to figure out what is on an image and what not. And now some people always, or my students actually sometimes come to me and saying, come on, in the age of large language models, we don't care anymore about that. But that's actually a graphic from G's free training data cleaning pair plan, which also shows that also for training large language models, there is a lot of pre-processing involved, right? It's not like some people simply grab all the text from the internet and are done with that. The first steps are a lot of transformations of that kind of data before they're really starting to do the machine learning model training. So that stays as one of the big challenges actually in the field. Next, after we have our pre-processed our data somehow, we have to think about the model selection. What kind of model would we actually do? And that's actually what the machine learning, the AutoML community did for quite some time actually. As one of the core problems, more or less. One of the first papers in that direction was AutoVeka, more than a decade ago, won our best time award prizes and so on. Simply saying, okay, let's decide what is the best machine learning model at hand by searching over different kind of things, trying that out in an efficient way. And these days get actually more complicated, because if you go in these days to Hugging Face, it's not talking about more tens of different models, because now we have pre-trained models, and maybe you'd like to do some fine-tuning or in context learning or whatnot, right? You still have to decide actually from all these models actually which one to take. And now we have 1.7 million models available. Of course, you can then classify that on your task, but nevertheless, it's an enormous amount of models being available these days, and we have to navigate through that. So that problem is actually more problematic than it was ever before. Why is it not? What happened now? That's not good. I fully agree. Here we go. AutoML optimization. As the next point, so now you decide for one model, right? You know what kind of transformer, what kind of CNN, what kind of REST and whatnot, right? You decide for that. Now you're going actually for deciding how to train it, for example. And if you're looking at the documentation actually, for example, only of SGD as the basic things how to train a neural network, right? You see already you find 5 hyperparameters being involved in that. And Of course, for standard architecture, for standard data sets, if you're always doing experiments on C510, that might not be super interesting for you. But the moment you're going away from these kind of standard data sets, then you have to deal with that over and over again. And actually, if you think about the complete pipelines being involved and so on, you can go easily beyond 30 hyperparameters, as several studies showed before. So what we did actually some time ago, I think it's now roughly 2 years old, was writing an overview paper survey actually on how to do different kind of hyperparameter techniques. Bernd will also tell you a bit more later in this talk in the next session. Then the architecture search was the next big thing actually, because you don't only want to select actually a model, but if you selected a model, you now would like to decide actually what is the size of it, what kind of operators actually you need in that. And that was enabled more than your architecture search. And there are always more or less two views more or less on that. And on the one hand saying, okay, you would like to think about the overall big picture of the architecture and say, okay, I don't know how many attention layers you need and so on. So more as really thinking about the big picture and saying, okay, what you need overall. For example, back then we always talked about how many reduction cells, normal cells we need to stack on top of that. Or you can really think about the details. So each of these cells in the end is then more small part of the neural network where you always already have all the operators in that. So where you have all the pooling, where you have all the convolutions and so on. Where you need to think about how to wire all of that together. So you can optimize on that end, you can optimize on that end, and there are also some approaches these days actually on how to try to bridge actually both worlds together. And Aaron will tell you more about, I think, tomorrow morning, how to do that exactly. Then we go into pipeline design. So as I already argued before, right, data preprocessing is already pipeline-ish. And then you're putting actually a model to it and so on. So actually we care about eventually about the entire pipeline. We would like to optimize it together. So there was authors can learn, for example, by Matthias, who's also being here, very famous. T-Pont is very famous actually in the field, was saying, okay, we would like to very flexible pipelines, not only one lines through that, but maybe connecting and diverging and so on. So really having complex pipelines to it. Also in the direction ML Plan actually, there's a bit of full tree of possible preprocessing and model steps and so on. You have full flexibility by doing over these kind of things. Then let's talk quickly about approaches, how we can solve actually these tasks, right? I talked only about the problems we'd like to solve, but not how to solve them. First of all, black box optimization. One of the approaches for that is actually Bayesian optimization. Will be also covered by Bernd in the next session actually. In a nutshell, it's doing nothing else and saying, okay, we can observe some points describing given configuration what is the performance. And what we do as machine learning practitioners is always, of course, let's train a machine learning model on that and try to estimate how that kind of function looks like. We can do that by using probabilistic models. We can then trade off exploration, so going for complete new kind of settings, and exploitation, going more in the direction where we know where that should work well. And by doing these kind of trade-offs, playing with these kind of probabilistic models, we can do it over and over again and being very efficient in the end in figuring out, for example, what are good hyperparameters, what are good settings, even what are good pipelines. Now, some people of you might think, come on, why do I need this super complicated thing like Bayesian optimization? I'm always doing grid search. I would argue that it was already a paper more than a decade ago from James Baxter and Joshua Benjo showing or arguing why even random search is in most cases actually better than grid search. And then there was roughly 5 years ago a paper actually providing a lot of evidence actually with a lot of empirical studies showing that Bayesian optimization is actually a lot better than random search. So if you really like to go for something efficient, don't wasting time, don't wasting money and compute resources, I would already argue Bayesian optimization is much better than grid search or random search. Then, of course, what I should not forget to mention is evolutionary algorithms are also very famous in the field. This idea of, say, okay, you have a population of configuration, you're doing some kind of rotation crossovers going for selection based on that and going over and over again, more as nature more or less would also do it. There's a lot of approaches actually being involved. And the funny thing about that part, from my experience, is that people rediscover evolutionary algorithm over and over again. So maybe when the community more started, Teapot was already using some kind of EA for that. Then more or less for neural architecture studies was rediscovered, oh, we can apply EAs to that. Very simple ones actually. And I would argue that also what people partially doing these days with alpha evolve is also again more picking up ideas from evolutionary algorithms again very simple ones, and trying out these kind of ideas. So that's a cycle which just pops up over and over again, and in very simplistic ways actually. The next is multifidelity, and here the underlying idea is saying we know a bit more about machine learning, and as you would actually not run all your model trainings until the end, but you observe a learning curve, so how it progresses over time. So you're doing some epoch training, you're seeing already, is the model picking up? Is it really learning something? If not, you simply stop that. Multifidelity optimization is doing the same, simply by saying, come on, I'm comparing different kind of model training runs after a few epochs, I'm discarding some of them. And then I go on with the promising ones, at some point I discard more, I go on with the promising ones, and so on. And the nice thing is we can see actually that it works on a lot of different kind of scales, on a different kind of models. It's not only on neural networks, it can also work even with traditional machine learning models, even if we're applying XGBoost or random forests. And you can do it also with different kind of fidelities. You can do it with model training. You can also do it with data size, so simply starting with more data and then going for larger data. And so you have different kind of possibilities. You can also start with a small network and going for larger networks from time to time, right? So anything which gives you more complexity over time can be used in multi-fidelity optimization. And then, of course, you can combine it again with ideas what we had before. You can combine it with spatial optimization, and you have Bob, for example. You can combine it with evolutionary ideas, for example, with STEP, but many others. You can also go for highly parallel approaches, and you have Asha actually. And there's a lot of combination actually. Was a big trend roughly, I don't know, 6 to 8 years ago. And then the big topic actually these days is, has a lot of people trying to use large language models for helping with all the optimization. A lot of papers coming out. First of all, I would like to say, unfortunately, there's a lot of papers not comparing against methods 5 years ago. So a lot of people now starting again with very trivial baselines. Nevertheless, there's quite some nice ideas around floating. And I would like to start actually with pointing out that LLMs can help with a lot of different kind of problems, right? Of course, you can see in large language models an interface. That's maybe the most trivial view on that. You can see it actually in deciding, okay, what is actually the configuration space you are talking about? Do we really need to talk about learning rate and batch size, or maybe batch size is not important? How can we use it directly as a component in the optimization approach? So it can also help to suggest new configuration or helping with the evaluation and simply not really doing the training of the machine learning model, but simply asking the large language model doing that. It can also help for interpretability and so on. So there's a lot of ideas actually on how to combine that. One few very concrete ones. For example, the Café paper, again by the colleagues from Freiburg, was quite nice because it was more doing a lot of data pre-processing issues, large language model, feature engineering and so on ideas. There was a very nice paper by Michaela van der Schaar's group actually, I think now 2 years ago, on Lambo, which used more or less a large language model as a substitute, as a surrogate model in Bayesian optimization ideas, and then also iteratively trying to figure out, okay, what works better, and asking the large language model over and over again, also trying to more imitate this kind of probabilistic behavior. And quite nice, also very recently, was a Limbo paper, then trying to show actually how we can, in different ways, integrate large language model into Bayesian optimization to say, okay, can be helped for suggesting new configuration or as constraining and filtering certain configurations, was also quite nice, I believe. Okay, next thing which I should really definitely mention here is multi-objective optimization. Because in practice, the machine learning community, and if you're going to NeurIPS, ICML and Co, most paper makes very easy what is not working in real life. Because we can't always simply talk about accuracy or perplexity and only looking at one specific metric. If you go to industry, what we observe is most people care about more than one objective. They care about several things. They need to care about several things, right? So they would like to be accurate, but they also would like to think about the hardware they're running on, how to be efficient on that. What does it mean also for inference times? If you would like to go large scale, you can't simply waste a lot of computer resources. You need to be very efficient. Inference times have to be very small. But also from a legal point of view and an ethical point of view, you have to think about fairness. What is your model discriminating someone? Maybe you have to think about interpretability. What happens if someone is suing you? Or what if some of your customers would like to know actually why is making these kind of decisions now for you? You have to think maybe about robustness, right? And so you have to think about a lot of things in practice. You can't only think about accuracy. And multi-objective optimization actually helps you with trading off these different enough objectives that you have the possibility to make an informed decision how you can trade that off. Because on the one hand, of course, you would like to make all models much bigger because much of the time larger means more accurate. But on the other side, that means also we have more poor inference time, for example, right? We are less efficient with that. How to trade that off? Multi-objective optimization can help with that. Then talking about foundation models, which is of course also something which is more and more important these days. Because to some degree, foundation models can help you with taking care of a lot of things. For example, the paper above is the Nature paper on top PFN, and they more or less argue they can train a model, a foundation model, which simply takes the data set, completely as an input, doing one forward pass and giving you predictions. So you don't have to do any kind of training anymore because the foundation models beforehand took care of that. So that is in principle a very powerful thing to do. Comes with some limitation, and you have to be careful also with doing that. But in principle, quite a nice idea. Chronos, for example, is doing the same thing for time series data, right? Also here again, foundation models, you're feeding in your data, getting direct predictions. You can also combine these kind of ideas with spatial optimizations. So say, okay, if you have these very strong foundation models, why not doing it directly as part of your optimization loop? Also being done. Good. Then we talk about that first part. What happens most of the time as a post hoc step later on is then you have a lot of models, you have trained something, you know what performs well. Why not combining several models? So we did that already for quite some time actually. Combining ensembling was a technique. Autocluon's approach, at least in the tabular case, the most famous one right now, they're using a very specific way of stacking actually. So you have your input, you have several models, you're getting predictions, you're getting all of these together. So your input and the predictions, you're concatenating them, feeding that in again to all your models, and then again a weighted ensembling all of that. So you stack more or less the entire process. Quite powerful, can do a lot of things for you. But of course, you can also ensemble large language model, and that can also help you, right? So that's not the one large language model, the same way this is not the one machine learning model. All of these models have their strengths and weaknesses, and also here ensembling can help. But you also have to consider again, in a real world scenario, that costs you compute power, right? These models are getting bigger. So you're trading off accuracy again with, for example, inference time or memory consumption. And then what we, for example, in my group, and I know that Bernd group also cares quite a bit about, is our interpretability, because we would like to explain actually what goes on, especially people using also AutoML would like to understand why there was certain decisions. And so we work on different kind of approaches in that field actually. So for example, what Frank did, Frank Hatter in Freiburg, when he was more very connected still to UBC, was thinking about functional ANOVA, how to apply that and assessing what is an important hyperparameter. We were thinking about partial dependence plots, for example, and say, okay, we would like to slice through one of the hyperparameters and say, what's the effect of that? Can we do that? When is that reliable, and under which circumstances? We can, of course, also go for symbolic expressions, because most of the times, if you're reading a paper and on the level of hyperparameters, you have somehow an equation describing things. So can we try to discover these kind of equations also? The symbolic equation, we also try to do that one. Or we're seeing, presented by Max, I think, also tomorrow, Shapley values, right? And Shapley values, for example, can also be used to explain what are interactions between hyperparameters, what are important hyperparameters, and so on. So a lot of things you can actually learn also from AutoML. It's not only press button technology that is doing a lot of jobs for you, it can give you also insights actually at the end of the day. Next thing I would like to briefly mention is that benchmarking is very important. Kata mentioned that she is very interested there, and Matthias is also very much into the topic of benchmarking actually, because the AutoML field is doing partially also theory, but it's quite driven by empirical results, right? You always try to say we developed approaches which improve performance overall. So we care quite a bit about benchmarking. And this community also developed a lot of things over the years. For example, very famous is all the entire series of NAS bench. So for neural architectures, there's different kind of benchmarks where groups sit down, for example, matters a lot of different kind of architectures, record all the performance values, make them available, that you can, for example, do that very quickly without investing a huge amount of compute power. On the HBO side, for example, there was HBO bench in the Apo gym, also provided a lot of different kind of benchmarks tasks for HPO and so on. And what we recently did, and Caro will also talk about that very briefly actually in the afternoon today, is CARBs, now being released since a few days, where we combine a lot of things. So you have a lot of hyperparameter optimization tasks, you have even NAS benchmarks tasks in there, and overall that provides 3,336 different kind of benchmarks being bundled in that kind of library now, which enables you to really try out a lot of things. Would like to know if you developed a new AutoML tool, whether it performs well or not. The last thing I'd like to mention is actually the user groups, because I think that's also what the AutoML community sometimes forgets. Who are our users at the end of the day, right? And it's not as easy as it may sound, because we could always say, okay, AutoML is developed for maybe people who have no knowledge about machine learning, who simply like to have a press button technology. And there are these kind of users, really like domain experts from science or from other fields, where you don't have the technical background to go into all these details. That's quite nice. But on the other side, we also have a lot of users from the machine learning and data science field, right? Who are experts, nevertheless would like to make their life easier, more efficient using all these techniques. And for all of these different kind of users, there are different kind of needs and perspectives actually we need to address. So we need to think about, okay, what does it mean for the domain expert? What kind of explainability, what does they need actually? For the typical data scientists working at a company, what are they needing? They care maybe about quite some understanding of on bias or validating your model. An AutoML expert would like to develop an AutoML tool, does need something else, right? They care much more on the meta level of thinking, okay, what kind of page optimization approach maybe I need. The data scientist maybe also nevertheless later on then needs to think about ML ops, so everything also involved with deployment and so on. So there's a lot of different stakeholders being involved, and if they would like to use AutoML techniques, we need to develop also these kind of AutoML tools in a way that we can address many of them, that we are flexible in that sense. And I have to admit at that point that we are only at a starting point to really go for that kind of vision that we can address all these kind of different stakeholders. That's the weakness of the AutoML community. With that, I covered very briefly that entire picture. I think that as for the first few minutes enough that you can process and think about that and have a starting point for everything. But I have also to admit that's only the tip of the iceberg. That's not all. We did a lot more. The community did a lot more. There's a lot more to think about that actually if you think about AutoML. So there's more to it, and you will learn also more than I covered here in that talk actually during that week of the AutoML school. Nevertheless, I would like to point out to a new website we launched at the beginning of this year, which is called AutoML.space, where we have a hub for AutoML content. So we try to connect a lot of things, whereas events, it's software packets, it's a lot of videos from different kind of AutoML schools and conferences and so on. We link into the AutoML seminar, to online courses, to the AutoML podcast and so on. So if you'd like to learn later more about AutoML, after you are hopefully very inspired and motivated after this week, go to AutoML Space and you will find a lot more of tools, packages and so on, which maybe and hopefully help you in your future. With that, I'm done. Thank you very much. Are there any questions?